Hello everyone, I'm Tim Lichtenberg from Oxford, and I work on the formation and early evolution of terrestrial planets in the atmospheres. My principal goal is to better understand the early formation and evolution phase of terrestrial planets in order to infer something about the planetary environment of the Hadean Earth, with the ultimate goal of better understand, what was the environment that enabled the origin of life on Earth. But I think we should look out in order to infer something about ourselves. Why is that? So what you see over here on this slide are two contrasting scenarios of the Hadean Earth, which was a very defining phase on Earth, and we have no geological record of this. And there's basically 500 million years directly after Earth's formation that are completely gone and vanished from our sight. After the Apollo mission, we had this picture of the Hadean Earth, very hellish, frequent meteoritic bombardments, constant volcanic outpourings. But since evidence for liquid water at the Earth's surface emerged about very rapidly after the moon-forming impact, in fact, that picture is, in question. But still, we have very little that can help us from a geology point of view. And so what we are aiming to do is to actually look to other planetary systems that are still currently in that phase and that are young, and that can inform us about how terrestrial planets at that stage of evolution evolve and how they look like. Principal questions are, of course, for instance, the composition of the atmosphere and the interior that can help us to inform the geochemistry of the surface at that stage. Why is that important? So for instance, here you see the interior. The interior composition determines the amount of gases or the composition of the gases that is degassed and forms the atmosphere. The atmosphere itself is also, of course, very important because it kind of sets the UV environment of the surface. It gets influenced by the radiation environment from the star, and it can directly react to changes, but for instance, from bombardment, cometary or meteoritic bombardment. Now, those two things together make up the geochemistry of the surface. This directly affects the feedstocks that are available for prebiotic chemistry. So the combining link here is the redox state, and all of them are set and are affected and affect themselves the redox state of the mantle and the prebiotic chemical networks that can play out on a given planet at a given stage. Now, what you see on that next slide is a sort of confusogram, but it shows one envisioned pathway of how terrestrial or rocky planets in general acquire their atmospheres. So this is time, and this is the interior, and this is the atmosphere. In the beginning, it's thought that terrestrial rocky planets, specifically larger ones, still have hydrogen-rich atmospheres that are directly sourced from the protoplanetary disk. The mantle is molten because from its accretionary heat, but then solidifies over some time. The primary atmosphere is lost due to escape, and then is replenished from volcanic outgassing. That is why the composition of the interior is so important, because it sets the composition of the gases that are released to the atmosphere. Now, this story can be different depending on the composition of the planet, and therefore depending on the specific accretion path of the planet itself. And this changes very dramatically how these planets evolve during their earliest phase. So here, for instance, you see the cooling from magma ocean to a habitable planet. This is surface temperature. This is cooling of the planet via heat loss through the atmosphere. And depending on the primary composition of the atmosphere, for instance, if it's H2O dominated, O2 dominated, CH4 dominated, or H2 dominated, the heat loss is dramatically different, several orders of magnitude. This has very severe consequences for the surface environment, for the geochemistry of the mantle, and for the composition of the long-lived atmosphere. Now, that's why we develop computational models that actually can quantify the differences between those scenarios. This is what you see here on the right. You see basically the evolution of a magma ocean planet, in this case an Earth-sized one, for an H2 and an H2O dominated atmosphere. So this is temperature in K, depth in mantle, height in atmosphere, and you see the difference in cooling behavior of an H2 and H2O1 from 100 year to 1 mega year. And you see that after 1 mega year, the surface temperature is strongly different, very strongly differing, and also this stratification of the atmosphere is different. And these differences are so strong that they are on the order that we can potentially resolve with astronomical surveys. Not only the size is so strongly different, but also the planet looks very differently. This is shown on the left-hand side, contrasting H2O again with H2. The y-axis here is the spectral flux density for a given wavelength. This is basically how the planet looks like. So astronomical surveys only probe a specific length or a specific area of that wavelength range. And this here, for instance, is the wavelength range of of a future direct imaging survey that is currently in the concept phase. And these types of astronomical surveys will not only be able to actually see those types of planets, but they will also be able to infer something about the interior state. And these are the different lines you see here. So I don't have the time to really go into the details, but these different lines show different interior properties. For instance, how the magma and the solid rocks behave. And you see there are order of magnitude differences for differing crystallization path and order of magnitude differences between compositions of the atmospheres. And so when we will be able to see those planets, we will be able to make out their differences and understand the diversity of these early proto and cooling magma ocean atmospheres. Now this is for the future, but at the moment the question is really how do larger planets behave? This is potentially important because some of them, specifically this class of so-called super-Earths or sub-Neptunes, is dominated by rocks by mass, and so they are definitely related to the terrestrial planets to some extent. And we can actually probe them today, and specifically with the James Webb Space Telescope from next year on. This here shows these are two famous members of this class. This is GJ1132b, for which there has been a claimed detection of a reduced atmosphere. This is K218b, for which there's evidence for water in its atmosphere. And the existence of these types of super-Earth atmospheres is very important, specifically the long-lived ones after the proto-atmosphere has escaped, because we can then, if they are reduced super-Earths, we would be able to probe prebiotic chemistry in action. This here, for instance, is a model spectrum of this planet, GJ1132b. And you see that, for instance, with JWST NIRCam instrument, we would be able to make out cyanoacetylene in the atmosphere using different markers. So this is something very exciting to look forward to, and potentially in the next few years we will actually get confirmation of these types of observations. Now, this is exciting, but it's debated in the community. And the reason, one of the reasons, is that we actually believe these secondary atmospheres in super-Earth should not be reduced; they should be oxidized. Why is that? The reason is that larger planets should, in principle, tend to be more oxidized because of geochemical reactions that operate in the interior of these planets. So the principal idea is that if you have like something on the order of a moon or Mars-sized planet, you can host a reduced atmosphere, but the larger you go, the more oxidized you become. And one of the main reasons for that, specifically relevant for Earth-sized planet, is iron disproportionation. The principal reaction here goes like this. So react Fe2+ in Fe2+ phase to Fe3+ plus a metallic iron. For instance, where the reaction silicate melt plus aluminum oxide makes perovskite plus metal. And this metal, due to gravity, then sinks to the core, and this net oxidizes the mantle, and this means that the gases that come out of the mantle are rich in water and carbon dioxide, for instance. Now, that is the standard picture, but it may be fundamentally different in super-Earth, actually. This is what I've shown earlier this year, because the super-Earths are much larger and their gravity is much higher. The convection in the interior is actually much more vigorous. And people have not quantified this so far, but it turns out, using scaling analysis, that the convection is so vigorous that these metal droplets don't have to sink actually to the mantle, and they don't merge with the core. That means that reducing power can be kept in stasis in the mantle, and therefore super-Earth can still, in principle, host reduced atmospheres with H2, CH4, and NH3, and their photochemical derivatives. And this predicts that actually, if the magma ocean dynamics in super-Earth should work like this, then we would expect to see reduced surfaces, versus in this case we would expect oxidized surfaces. And because this scenario enhances the chances for detection on long-lived reduced atmospheres, we should in principle be able to probe this with near-future observations. Now, the prospect for observing surfaces is actually very exciting, and it probably has been done already. for the specific famous case of LHS 3844b, here you see a temperature map of the planetary surface from a very long Spitzer Space Telescope campaign. And this was the first planet for which we have actual temperature boundary conditions now from this temperature map here. So here's the star. This planet is tidally locked. Its surface, its star-facing side is in an eternal day. It's hot but not molten. And the night side is eternal night, and it's freezing cold. There's no atmosphere around, so it's basically direct space boundary conditions. And because this was the first time we actually have a boundary condition for a super-Earth, we use that and try to infer the geodynamic mode of that planet. It turns out it's fundamentally different from anything that we see in the solar system. This is what you see over here. So here's the star. This is a cut through the planet. And this is the geodynamic model. So what you see is basically the flow of the rock inside. This is solid state convection. Here's the metal core, and here's the surface of the planet. You see upwellings on the day side and cold downwellings on the night side. But this is actually not our preferred model because we think that the lithosphere on these types of planets should be very strong. And in that case, something very unintuitive happens, namely that actually the day side is the prominent location for downwellings, and the night side actually should feature more upwellings and therefore also volcanic outpourings. And this actually predicts that the volatile recycling pattern on these types of planets should go like depicted here, so from the day side down to the mantle and through volcanic outgassing be released again on the night side. And this is again something that we will be able to observe with JWST. Specifically, this planet is targeted for an observation campaign next year. And with that, I want to finish. And just to summarize, so hopefully we will be able, using astronomical observations, to infer the composition of secondary atmosphere, which constrains the mantle redox state and volatile budget, and tells us something about the interaction with hot molten mantles and the atmospheres, and therefore informs the planetary environment of the Hadean Earth. With that, I want to thank you very much for your attention.